I have a pretty interesting attention experiment here that's very simple, but it will help you master attention. You've never seen something like this. So we have input of three numbers, let's say 2, 8, and 5. And we need to use attention mechanism to find highest number in this sequence. So this is the idea. You know that this number 2 will pay attention to itself, all of the three numbers. And then this number will pay attention to all of the three numbers, and this number will pay attention to all of the three numbers. And the idea is to make that each of the numbers pays attention to the highest number in the sequence. That's what attention mechanism will do. So in this experiment, these are the results. For position 0, here number 2, this pays attention to the second number. You see 0.999, and then almost 0 to the other two, which is correct. The second number is highest. And for position 1, number 8, it's correct as well. So number 8 also pays attention to itself. And number 5 also pays attention to number 8. So this is successfully trained attention mechanism. First of all, I want you to think about this. So it's gonna be the same as tokens in large language model or any other attention, image generation, everything, diffusion, everything. They all use attention. So I constructed this loss function so that we teach it to pay attention, to transform its weights, so that attention is paid to this middle number. And the way it works right now is very simple. Actually, I'm not even using value. I'm just using query and key. And then I'm just finding the attention between all of them by multiplying query and key. So what does that mean? So I just have one number as input, which is going to be the value of whatever the value is of that number. So 2, 8, and 5. And then we are projecting that to the vector of 4. So the length of query and key is going to be 4. It's a vector of 4 dimensions. Here you can see on the side, this is the final weights of the query and weights of the key. And this is the learning process. And these weights are going to be same for every input. Just depending on the input, they're going to create some different inner dimension. So these weights multiply this input, which is going to be 2, 5, or 8, or whatever number between 0 and 9 in this case. Multiply and then create some inner dimension. And you see how they are evolving over training. So both of the query weights and key weights are evolving in some way that when they get multiplied with input and produce the embedding the queries and keys outputs, depending on the input, the queries and keys are gonna have dot product high at the place of the highest number and low at other places. So if this is a bit confusing, that's okay. I'm gonna show you more images and experiments to let you understand it better. So if we see how much attention it pays, you see here we have 5, 3, 6. It pays most attention to 6 because it is the highest number. So number 5 pays most attention to 6, number 3 to 6, and number 6 to 6. So all of them pay most attention to this number. But here is interesting question or problem. Why is number 0 paying equal attention to everything, every position? Try to find it yourself so you can understand this neural network better. Interestingly, Claude 4 Sonnet was not able to find it. It gave a wrong answer here. It's because when you are multiplying here 0 input times some weights to get query and key, both of them will be all zeros because 0 times some matrix. So you are just multiplying all zeros in query times all zeros in key. All of them are going to be zeros, and then the softmax will get 3 zeros, and then it will just convert all of them equally to add up to 1. This is an example of when input numbers mess with neural network. So other examples are exploding gradients, where if these input numbers are you have 5, 5, 2000. So the gradient with respect to the weight that multiplies 2000 will be huge, because if you change that weight a little bit, the loss, the result will be hugely different. So that gradient will be huge with respect to that weight, and then neural network will try to update that weight a lot. This is something that muon optimizer, for example, solves. But more about that, you can learn about muon optimizer in my videos, for example. So my point is that gradient is not big because that weight, changing that weight will improve the loss, make the model learn. It's just big because this input number is randomly arbitrarily high and not because the weight is good for learning. Let's see next thing. I trained it only on whole numbers. So what's gonna happen if I put 4.9, 5.1 and 5? So just 0.1 difference. Let's see the attention. So 026, 041 and 032. So this shows how neural networks generalize. So it's correct and I like it. So this is correct. But it's not like 010, the huge attention difference. So you can see that these learned weights of key and query are quite low. Red in this case is low. But if I train again, do you think they will stay the same or be different? I think they will be different because this process is random. Yeah, so they're different now. Now they're a bit high. Blue is high. What if I put two negative numbers and you see 7 and 5 look like big numbers, but they're negative, and 1 is actually the biggest number? I think it will still work though. It works. Oh wait, it got confused here. So -7 pays most attention to itself. So it thinks that -7 is the highest number, and position 2 thinks that -7 is the highest number. That's crazy. While position 1 correctly guessed itself. So what does that mean? So I have two findings in these two experiments. I just swapped. I swapped number 1 and number -7, and the same thing happened. Both of them guessed itself, as in the first place. The same scores, the same numbers. Everything same, just the places are now swapped. So I have a theory that we will test. Maybe the way neural network learned to pick the highest number is which number is furthest away from 0. And now that we introduce negative numbers, now they mess with this, what network learned. So I did experiment with 3, 1, -3, and it looks like number 3 is paying attention properly. Number 1 is also paying attention properly, although it's less confident. But number -3 has it flipped. So maybe this, no, actually number -3 is just paying attention to itself. It's not even flipped. It's very strongly paying attention to itself. So maybe this minus is messing with the calculation. So this experiment disproves distance from 0 hypothesis because there is no symmetry between plus and minus x. It's not the same. Here's what we see. We see practically 0 attention between positive and negative pairs. So 3 gives almost 0 attention to -3 and save for the other ones. And then strong self-attention for both extremes. But the middle value 1 gets less attention than the extremes. So the model is recognizing number 1 as the less of the +3, +7, but also as the less of -3, -7. So whatever is messing up with negative numbers, it's looking at negative numbers that have absolute value higher than 1, that they actually are higher than 1, but they're not. So it looks like positive and negative numbers don't see each other, as if they don't exist. So -3 doesn't see 3, as if number 3 doesn't exist. Now this is interesting. I have -5 and 5, but I have -1. So what's gonna happen now? Of course, -5 will vote for itself and 5 will vote for itself. But -1 will vote for -5, which is interesting. It looks like negative numbers don't even see positive numbers, and positive numbers don't even see negative numbers, which supports Claude Opus' hypothesis that positive and negative values don't see each other, which is actually AI helping to do AI research. It's not even just coding, it's actually in thinking as well, because Claude Opus has been recommending a bunch of these experiments that I was doing as well and drawing conclusions. and I was just managing and working with it. So this is an interesting theory by Claude Opus. So these query and key matrices are only trained on positive numbers. So when they encounter negative numbers, they see them in completely different space, in completely different way than the positive numbers. So maybe a query of a negative number will nullify key of a positive number. So they will produce result 0 and vice versa. So model has learned to process negative numbers completely separately in a complete separate function, complete separate attention mechanism than positive numbers. So we will test this hypothesis right now. How would you test this hypothesis? Well, I'm asking Claude Opus, to be honest. I used Opus to tell me what to do. I used Sonnet, copied the output into Sonnet to generate code, and then copied the output of the code into Opus to generate the report. This research is so easy. And Opus said, fascinating discovery. And the model learned perfect sign inversion, not orthogonality. So, key of minus x is equal to minus key of x. And same for query. So it is true that positive and negatives don't see each other, or don't pay attention to each other, I should say. Because if both numbers, if number for the query and number for the key are positive, then we get high attention. If both numbers are negative, it's gonna be same as removing those minuses. It's gonna be same as just doing it with two positive numbers, so high attention. And if we have positive and negative number, it's gonna calculate the dot product, but there will be a minus before it, so negative value, so low attention. Now Claude Opus is talking as if this is a good thing, but maybe it forgot that model failed with this. It's saying like, oh, this is efficient way to do it, blah, blah, blah.